Introduction to DNS-based ALPN. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring DNS-based ALPN discovery, which represents a significant evolution in how clients discover and connect to services on the modern internet. Traditional ALPN, as we've discussed previously, happens during the TLS handshake where the client and server negotiate which application protocol to use. However, this traditional approach has a limitation. The client doesn't know what protocols the server supports until it actually initiates a TLS connection. This means the client might attempt connections that are destined to fail, or fall back to less optimal protocols, wasting time and resources in the process. DNS-based ALPN solves this problem by advertising protocol support information directly in DNS records, specifically through two new record types: SVCB, which stands for Service Binding, and HTTPS records. These record types allow servers to publish rich metadata about their capabilities before any connection attempt is made. Think of it like checking a restaurant's menu online before you drive there, rather than discovering they don't serve what you want only after you've made the trip. With DNS-based ALPN, a client can query DNS and learn that a particular service supports HTTP/3, HTTP/2, or other protocols, along with additional connection parameters like port numbers, IP addresses, and ECH configurations. This approach is defined in RFC 9460, which was published in November 2023, making it a relatively recent addition to the DNS ecosystem. The SVCB and HTTPS records don't replace traditional A and AAA records. Instead, they complement them by providing additional service metadata. The HTTPS record is actually a specific type of SVCB record optimized for HTTPS services, making it easier to adopt for web infrastructure. These records enable what's called optimistic connection establishment, where clients can make informed decisions about which protocol to attempt first, potentially saving an entire round trip compared to traditional fallback mechanisms. This is particularly valuable for HTTP/3, which runs over QUIC and uses UDP instead of TCP, requiring a fundamentally different connection approach than HTTP/1.1 or HTTP/2. SVCB and HTTPS record structure. Let's dive into the structure of SVCB and HTTPS records to understand how service information is encoded. Both record types share the same fundamental structure, with HTTPS being a special case of SVCB, specifically for HTTPS services on port 443. The record consists of several key fields that work together to provide comprehensive service information. The first field is the priority value, which is a 16-bit unsigned integer. A priority of 0 has special meaning. It indicates an alias mode where this record points to another name that should be queried for the actual service parameters. Any non-zero priority indicates service mode, where the record contains actual connection parameters. The second field is the target name, which specifies the domain name of the service endpoint. In alias mode, this is the name you should query next. In service mode, this is typically the actual hostname of the server, though it can be a dot, which means to use the query name itself as the target. Following the target name comes the most interesting part: the service parameters, encoded as a series of key-value pairs called SVC parameters. Each parameter has a numeric key and a value whose format depends on the specific parameter type. These parameters are what enable the rich metadata that makes DNS-based ALPN so powerful. The most critical service parameter for our discussion is the ALPN parameter, which has a key value of 1. This parameter contains a list of ALPN protocol identifiers that the service supports, exactly like the identifiers we discussed in traditional ALPN. The list is wire format encoded, meaning each protocol identifier is prefixed with its length as a single byte, then followed by the protocol string itself. For example, if a service supports HTTP/2 and HTTP/3, the ALPN parameter would contain the encoded strings H2 and H3. The order of protocols in this list indicates the server's preference, with the most preferred protocol listed first. Other important service parameters include port, which specifies an alternative port number if the service isn't on the default port for that scheme. The IPv4 hint and IPv6 hint parameters provide IP addresses that clients can use to optimize connection establishment, potentially avoiding an additional A or AAA query. The ECH parameter, short for encrypted client hello, provides configuration for encrypting the TLS client hello message, which is crucial for privacy. The mandatory parameter specifies which parameters a client must understand to use this service record. If a client encounters parameters in the mandatory list that it doesn't understand, it must skip that particular service record and try another one or fall back to traditional resolution. This ensures that new parameters can be added without breaking older clients while still allowing servers to require support for critical features. DNS query and response flow. Understanding how DNS-based ALPN works in practice requires examining the complete query and response flow. When a client wants to connect to a service, the process begins with a DNS query for either an HTTPS record or an SVCB record, depending on the service type. For web services, clients typically query for HTTPS records, since these are specifically designed for HTTPS connections and are easier to process. The query itself is a standard DNS query, requesting the HTTPS record type, which has the numeric value 65 in the DNS protocol. Modern DNS resolvers understand these record types and can process them just like traditional A or AAA records. The DNS server responds with one or more HTTPS records if they exist, or returns an empty response if no such records are configured. This is an important point. DNS-based ALPN is entirely optional and backward compatible. If a server has not published HTTPS records, clients simply fall back to traditional resolution with A and AAA queries. When HTTPS records are present, the client receives them along with their priority values and service parameters. The client then processes these records according to their priority. Records with lower priority numbers are preferred over those with higher numbers. If multiple records have the same priority, clients can use them in any order, enabling simple load balancing at the DNS level. When processing a service mode record, the client extracts the ALPN parameter to understand the protocols the service supports. It also examines other parameters, like IPv4 hint or IPv6 hint, to potentially obtain IP addresses without additional queries. If the client supports one of the advertised ALPN protocols, it can proceed directly to connection establishment using that protocol. For HTTP/3, this means the client can immediately attempt a QUIC connection on UDP port 443 without first trying HTTP/1.1 or HTTP/2 over TCP. This is the key optimization that DNS-based ALPN enables. The client makes an informed decision upfront, rather than discovering protocol support through trial and error or waiting for an Alt-Svc header in an HTTP response. If the client encounters an alias mode record, indicated by a priority of 0, it must perform an additional DNS query for the target name specified in that record. This aliasing mechanism is useful for several scenarios, such as when multiple service names point to the same infrastructure or when using CDN services that provide their own service names. The alias can point to a name in a different zone, enabling flexible service delegation. Once the client resolves the alias and obtains service mode records, it proceeds with connection establishment as described earlier. Throughout this process, the client must handle various error conditions gracefully, such as malformed records, unsupported mandatory parameters, or complete absence of HTTPS records, falling back to traditional connection methods when necessary. Benefits and real-world deployment. DNS-based ALPN provides several significant benefits that improve both performance and functionality for modern Internet services. The most obvious benefit is connection optimization. Clients can avoid wasted connection attempts by knowing upfront which protocols a service supports. For HTTP/3 in particular, this is transformative. HTTP/3 operates over QUIC on UDP, which is fundamentally different from the TCP-based HTTP/1.1 and HTTP/2. Without DNS-based ALPN, a client typically starts with a TCP connection for HTTP/1.1 or HTTP/2, receives an Alt-Svc header indicating HTTP/3 support, and only then attempts HTTP/3 on a subsequent connection. With DNS-based ALPN advertising H3 support, the client can attempt HTTP/3 immediately on the first connection, potentially saving an entire round trip and reducing connection establishment latency. Another major benefit is the ability to advertise multiple protocols with clear priority ordering. A server can indicate it supports HTTP/3, HTTP/2, and HTTP/1.1, all in a single DNS record, with the order reflecting its preference. Clients can then choose the best protocol they support from this list. This eliminates the need for complex negotiation mechanisms at the application layer. The service parameters also enable advertising additional capabilities like encrypted client hello support, specific port numbers for different protocols, and connection hints that reduce additional DNS lookups. These features collectively reduce connection establishment time and improve the overall user experience, particularly on mobile networks where latency is often a significant factor. From a deployment perspective, DNS-based ALPN is seeing increasing adoption, particularly among large content delivery networks and cloud providers. Cloudflare was one of the early adopters and uses HTTPS records extensively to advertise HTTP/3 support across their network. Google Cloud Platform and other major cloud providers are implementing support for these records in their load balancing services. The key to successful deployment is proper DNS infrastructure. Your authoritative DNS servers must support HTTPS and SVCB record types, which all modern DNS server software, like Bind, Power DNS, and cloud-based DNS services, now support. The records themselves can be configured through zone files or management APIs, just like any other DNS record type. However, there are deployment considerations to keep in mind. First, DNS caching behavior means that changes to HTTPS records may take time to propagate. This is controlled by the TTL values you set. Second, not all clients support HTTPS records yet. However, support is growing rapidly, with modern browsers and HTTP client libraries adding this functionality. Third, you need to ensure your DNS responses do not become too large. Very large DNS responses can cause issues, particularly over UDP. Each ALPN identifier and service parameter adds to the response size. So, it is important to balance the information provided with response size constraints. Despite these considerations, DNS-based ALPN represents a clear evolution in service discovery. It enables faster, more efficient connections while maintaining complete backward compatibility with existing DNS infrastructure and clients that do not yet support these new record types. Thank you for your attendance. Please consider subscribing to the channel.